Okay, so let's continue the proof from last time. Okay, so last time we showed that this inequality. So remember, like our goal, right? So for number yeah. So remember that our yeah. So remember that our can you so remember that our goal is to show that this remember that from last time we defined the C1 we defined the M to be the maximum over the function fd minus C1z, yeah. So our goal is to show that this yeah, so this maximum, whatever we define, yeah, okay, less than C1 R. Okay. All right. So yeah, last time we yeah. So remember we have the very like creative stuff that's it's not here. So it's gone. So yeah. So last time we have the equality modulus of C1 times R minus this M, which also depends on this small r, where this small r is like yeah. So yeah, this small r is being defined as I was making a mistake. I find 0 times r squared over 4m. Yeah, so this small r is like that. Okay, so yeah, so the thing is that this guy is what? So this guy is actually less than equal to f prime 0 modulus square r square over 60m. Okay. Yeah, it's bigger than equal to that. And then we define this one to be our rho, right? Yeah, so remember like so this one is equal to rho. Okay. Alright, so the thing is that yeah, so this rho is actually bigger than 0, right? So therefore, remember that originally, so the so result from part one implies that. So remember from part one we know that. Okay. The modulus of fd, which is so bigger than or equal to the modulus of c1. So I should add. So for any z in the closed disk at zero of radius small. Wait a second. Oh. Okay. Okay. Yeah. So yeah. So we have that. Okay. So less than C1. What? Hang on. Yeah. Okay. So I just copied down what I wrote here last time. C1 modulus Z times 1 minus is M. R modulus C1 times R. Right. Okay. So we show that this one is actually. Yeah, so remember that we are aiming to show, we are assuming that this one is, we want to show that fz is bigger than equal to 0, right? Or at least, yeah, we want to show that this vanish only at the origin. Okay, yeah, so yeah. Okay, so the thing is that you want to vanish, you want to vanish at the origin. This guy has to be bigger than 0, right? This one has to be bigger than 0. Right? Okay. So yeah, so namely this M arc must be less than equal to that, which we show here, right? Yeah, so which we show here. So yeah, so therefore so this notation. The closed disk counter at the origin. Okay. Yeah. Yeah. Okay. So all right. Let's see.
Okay, so what does this tell you? So remember that we have the Rauch theorem, right? So let me remind myself what is Rauch theorem. So suppose F, yeah, sorry, Fz and Gz are analytic on. Wait, what's that? On like a closed region, on this whatever gamma, right? So where gamma is a single closed curve, and Fz is bigger than Gz for z. A modulus of Fz is bigger than modulus of Gz for z in gamma. Then the functions fg plus gz and fz have the same number of roots inside the curve gamma. Yeah, the Rauch theorem basically says that you have two functions analytic over like a domain, or you can say that it's a domain, and then you have a simple closed curve over this domain. And then if you have the one function is big, the module of one function is bigger than the module of the other one for any point on this gamma, then these two functions, the sum of the two functions and the original f have the same number of roots on the curve. Inside the curve, sorry, inside the curve, yeah. So let me okay, yeah. Okay. Okay, no problem. Oh yeah. Alright, so okay, so why is that useful? Well, the thing is that here we know that we have this relation, right? So fz is, so f at 0 is equal to 0, right? So yeah, so basically we can, so see so basically we can compare these two functions, right? So yeah, so since fz is f at 0 is equal to 0, right? And modulus of f of z is bigger than modulus of 0, which is 0, on the boundary of yeah. Oh, okay. Yeah, on the boundary. Yeah. A single closed curve is at the interior. Okay, yeah. Alright, never mind. So yeah, so we can apply the Rauch theorem. So this implies that f z and oh, so it should be a contradiction, right? So think I oops. Sorry, forget about what I wrote. So actually the thing is let's see. Oh. Okay. So never mind. So let's see. Okay, so I want to say that f is bigger than equal to, so okay. Right. So okay. So it's not that simple. Okay. So it's not that simple. So okay. So let's further do something. Okay. So equal to modulus of C1 times modulus of Z times. So the denominator is the same, right? And then the numerator you have C1 R minus M R, right? Okay. So this one is bigger than equal to, of course, okay. Okay. Yeah. Rho over C1 minus R, right? So okay, we get that. Okay. Okay, so this is for any Z on the closure of the disk, right? So now for any Z, if the Z is on the boundary, right? So if the Z on the boundary, then this so for any okay, never mind. So for any so for any Z in the boundary of the disk of center zero, which is R, right? So the thing is that hang on, let's see. Okay, so so for Z and okay, okay, so this number C is equal to R, right? So we have okay, the modulus of FZ is bigger than equal to 0. Okay. All right. So yeah. So basically the thing, yeah. So the thing is that this one is bigger than 0. So so the idea is that so for any yeah. So W naught to be inside the disk centered at 0 of radius rho, right? Okay. Okay. So we have that. Okay. So we compare. So this is like a constant function. Okay, treat like a constant function. So when we compare this f and this w naught, right? So we have that the modulus of fz is bigger than or equal to the modulus of w naught, right? Because this w naught is inside the disk of radius rho, so the modulus of w naught is actually less than the modulus of rho. So therefore, this one is bigger than that. So this one is bigger than that. Of course, on this boundary, right? So I will use C0R for the boundary, right? So this implies that this implies what? This implies the function so by the Roche theorem, right? So yeah. Oops, I think that's a strict inequality, right? So because the modulus of W naught is strictly less than rho, right? Okay. All right. So keep that in mind. So what we finally get is, so by the Roche theorem. So do they annotate on the? So here I use the notation gamma like bracket, right? So like a bracket gamma. Remember this is how I define the Roche theorem. So okay. So I define the gamma closure to be like, yeah. So this is like the closure. Okay. All right. So yeah. So this is of course true, right? So the thing is that let's see. Where am I? Okay. So then, so this implies that this function. Wait. So I need the lecture notes. So this implies the. Wait, what? Hang on. Actually minus W naught. So why is that? Oh, okay. Okay, never mind. So yeah, so yeah, so just take this W naught to be negative W naught, okay? So think of it like a negative. So then by the Roche theorem, so Roche, this implies that this Fz minus W naught and Fz have the same root. So inside the curve, this one, right? Okay. So yeah, so we have shown that this so the number of rows that FZ on this disk, right? So because on any disk, we know that this FZ is, so we know that this FZ is not equal to 0 for any Z except at the Euler, right? Because yeah, because FZ is bigger than that, so which rho is a positive number, right? So y is no positive because yeah, f prime 0 is not equal to 0, right? And then this r is okay. So can r be equal to 0? If r equal to 0, then what is the okay? So the disk should be what is the point in the disk? Okay, okay. Yeah, well, this should be empty, right? What's the definition? Oh, what's the definition of disk? Okay. All right. Yeah. So yeah, we have nothing to show. Yeah. Yeah. All right. So wait. If okay, okay. So rho cannot be empty because yeah, otherwise f at 0 is yeah. Okay, never mind. So okay. Or let's just get rid of the r equal to 0 stuff. So yeah, so this one is what about m? Can m be equal to 0? Okay. M cannot be equal to 0 because otherwise f would be yeah, okay. Alright, so wait. Oh, okay, okay. Okay, never mind. So this m cannot be equal to 0. Alright, so the thing is that we are So the rho is must be bigger than 0. Okay. So yeah. So then yeah. What about the? Okay, the z is not equal to 0, right? For z on the interior. Yeah. So for any z on that on the disk closure, except at 0, right? So. Okay. So actually. Okay. Yeah, so this is something like the Roche theorem statement, right? So this is like something like or like another Strauss lemma, yeah, Strauss lemma. Okay, so okay, all right, never mind. So sorry, where am I? So yeah, so this FZ has is bigger than this guy, right? So it is which is some constant times modulus of z. So therefore it only equal to 0 at the origin, right? So then this same number of roots. Yeah, for yeah, so yeah, so for z in the closed disk of center 0 is R. And then this guy implies that this one has, so this implies oh, okay. Okay. All right, so yeah. So I feel like this is somehow yeah. I think that Roche theorem is kind of surprising that you get like the boundary behavior and then it tells some number of roots. Wait. Root means what? Root means it's 0, right? So this one and 0 or
Alright, so this implies there's only one root on this one. So yeah, so that this let's see, what's the original claim? So the original claim is for any W naught in this, yeah. Okay. Okay. So yeah. So any W is not in that. Okay. Yeah. Oh. Okay. So since FD is bigger than or bigger than, okay. Never mind. So okay. Yeah. So for any W naught, okay. Yeah. So this one has only one root. Okay. There it is a unique. Okay. Okay. Oh. All right. So yeah. So that's the proof. Okay.